So welcome back to Miss Riley's Maths videos. I've been asked to make a video about geometry for junior cert, but this would also apply to leaving cert geometry at ordinary level. And just to kind of work out what we have to do about these theorems, so in chapter 8 of text and test 2 on page 191, and then again in chapter 16 on page 386, there's the proofs of theorems. Now, on the new course that you're studying, you don't have to formally prove a theorem, but you do need to be able to understand what each of these words means: axiom, theorem, proof, corollary, implies, converse, and congruent. You may be asked about those, but you do not have to be able to do a formal proof, which is what your parents or your older siblings would have had to do. So that's good news. So what I want to do is, someone asked me to make a video and just say, well, how do we use these theorems? So you can see all these different facts here about isosceles triangles and transversals and parallel lines and parallelograms and so on. And then later on, similar triangles and congruent triangles and Pythagoras' theorem. And then over here, more proofs about geometry proofs about triangles and about parallelograms, and then the circle theorems. So there are plenty of examples in your book, in the exercises at the end of those chapters. What I'm going to do is I'm going to go through some questions that I've downloaded from past exam papers and work through them. And hopefully as I work through these, you'll kind of get an idea of how you use these theorems. Okay, so I hope this is what was being looked for. If not, you can get back to me. Okay, so here's a question here. It says the diagram below shows the parallelogram ABCD. Its diagonals meet at the point O. In this parallelogram, DAB, so that's DAB, is equal to ABC, ABC. So those two angles equal each other. Okay, prove that the triangle ABO is isosceles. Give a reason for each statement that you make in your proof. Hint, it may help to show that the triangles DAB, that's that one there, and CBA, that one there, are congruent. Okay, so the triangle ABO, we're trying to prove that that triangle is an isosceles. So what we're trying to prove is that triangle ABO, sorry, I'm just looking for my highlighter pen, which has vanished. We're trying to prove that the triangle ABO, this one here, ABO, is isosceles. And I think looking at it, we can say, well, it's probably proving that this side BO is equal to this side AO. Now, how are they suggesting that we do that? Where they're suggesting that it might help to show that DAB, that triangle there, and CBA, that triangle there, that they are congruent. Now remember, when it says congruent, they're talking about being exact copies of each other. And there's 4 different conditions: side, 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 angle, side, angle, or right angle, hypotenuse, and side, that we can use to prove that triangles are congruent. Okay, so maybe we might just go ahead and take their hint and try and work on that and see how we get on. And if that doesn't work, then we can come back and we can find another way to work on this. Okay, so let's just quickly as well run over what we know about parallelograms, because they've told us at the beginning that it shows that the parallelogram ABCD. So let's just do a quick aside here about what we know about a parallelogram. Normally a parallelogram doesn't look quite so like a rectangle. It normally has slanty sides. So if we have this parallelogram, what we know is that the diagonals of a parallelogram bisect each other. Diagonals of a parallelogram bisect each other. Now what that means is that this length and this length are the same, and this length and this length are the same, so that when they connect with each other in the middle, when they intersect each other, they split the other line in half. So looking at this one here, we know that this side here and this side here are the same length, and this side here and this side here are the same length. Now, what we're being asked to prove is that the triangle ABO is an isosceles. So we want to somehow prove that this side and this side are the same. This side and this side are the same. But as I said, let's start off and talk about DAB and CBA being congruent. So DAB and CBA. So what we're going to do is we're going to make a list of statements, and we're going to list them here, and they're going to match each other, and they're either going to go with side, 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 angle, or right angle, hypotenuse, and side. So I'm going to go, because look, this is one triangle, and this is the other triangle. I'm going to go with something that has an angle in it. Okay, so looking at this, I also know about a parallelogram, that the opposite sides of a parallelogram are equal in size. So I'm actually going to go with, I think, side, angle, side, side, angle, side. So let's start with this. So DA is equal to BC, opposite sides of parallelogram. And you see the way they said, give a reason, a statement for each, a reason for each statement that you make. So that's the first one. Now, what else do we know? We know that the size of angle DAB is equal to the size of angle CBA, or ABC, they've told us actually, because we're told that that was given to us, okay, up here. And then finally, we know that AB is equal to AB. In other words, this side that they both have in common is obviously the same length, side in common. So what have we chosen? We've chosen side, angle, side. Side, angle, side. So side, angle, side. DAB is congruent to, is an exact copy, CBA. Now, how is that going to help us? So we now know that this length AC and this length DB must be equal. So AB, the length AB, AC, the length AC must equal the length DB, as triangles are congruent. So they are the sides opposite this angle. This side is opposite this angle, and this side is opposite this angle. So they must be the same length, because those angles are the same size. Okay, so they're congruent. So therefore, if AC is split in two, in other words bisected, and DB is bisected, then both those lengths that they're split into, these two lengths and these two lengths, they must all equal each other. So we can say that OA equals a half AC, and that equals OB, which equals a half BD. So OA is equal to OB, so it's an isosceles triangle. Now that's quite a long proof. I suppose what helped us was that we did our congruent triangle first, and that's no harm to practice doing our congruent triangles. Okay, and then having done that, we now knew that these two diagonals were the same length. And then we were nearly finished, because if those two diagonals are the same length, then a half of one of them is equal to a half of the other one. And we've proved that those triangles are then, that triangle then is an isosceles triangle. Okay, so that's the first one. For our second question, this is going to be a theorem of Pythagoras question. It says, in the diagram below, the length of each of the sides is given in terms of x, where x is an element of n. Now, the reason I say it looks like it's Pythagoras is because it looks like a right angle triangle, doesn't it? And I've got a hypotenuse, and I've got two other sides. So it looks like that's right angled. And it says that the sides are given in terms of x, where x, so x is an element of n, means it's a positive whole number. So all these sides obviously have to be positive numbers. So x can't be 5 and x can't be 4. In fact, x has to be greater than 6 there, doesn't it? And it has to be greater than 4 there. So x has to be greater than 6 somehow. Otherwise, we'd end up with, well, x has to be greater than 5, I guess. Otherwise, we'd have to end up with a 0 there, okay? So we know that Pythagoras' theorem holds, so we know that the hypotenuse squared equals the other two sides squared. And let's just draw that, what that looks like. So CAB, so C squared is equal to A squared plus B squared. So in this one, x plus 4 squared is equal to x minus 4 squared plus x minus 5 squared. Now you can see we've gone straight away into algebra. So it actually isn't really a geometry question anymore, it's an algebra question. But we had to use the theorem of Pythagoras in order to find a way to set up an equation. Let's just finish this off. X squared plus 8x plus 16 is equal to x squared minus 8x plus 16 plus x squared minus 10x plus 25. So if you square this, you get this. If you square this, because remember, to square something means to multiply it by itself. X squared plus 4x plus 16. So x squared plus 8x plus 16. Okay, now, so what do I have? Let's remove the brackets. X squared plus 8x plus 16 is equal to 2x squared minus 18x plus 41. So putting that and that together, that and that, that and that. So what do I have? I'll bring all these over. Now really, hopefully, you know, if you're fine on your algebra, you may just want to have skipped on. But let's see how we get on. X squared plus minus 26x plus 25, isn't it? 25. So, what are the factors of this? X minus 25 and x minus 1. There's two numbers that multiply together to give 25 and add together to give minus 26. So x minus 25 equals 0, x minus 1 equals 0. So x equals 25 or x equals 1. Now, we said that it had to be greater than 5. So it can't be 1, because if it was 1, then I'd have 1 minus 5 equals minus 4, 1 minus 4 equals minus 3. I can't have two sides of minus 3 and minus 4. So I can't have x equal to 1, so x must be 25. So that would mean that my sides were, let's just fill them in. My sides were 25 minus 5, which is 20, 25 minus 4, which is 21, and 25 plus 4, which is 29. And those are that's the only value of x for which the triangle is right angled. Okay. Next one here. Again, we're still on triangles, but these aren't Pythagoras' theorem anymore. The diagram below is made up of two equilateral triangles and two parallelograms. 3 angles are marked, N, K, and M. Okay, so there's a triangle. It's equilateral, so let's fill that in. And there's another triangle, which is a bigger equilateral. So those two triangles will be what's called similar, won't they? They'll be similar triangles because they have the same angles. In fact, all the angles are 60. So let's just fill that in. 60, 60. Oh, we've already found K. So K is going to be 60 as well. Anyway, write the correct letter in each space to show what type of angle each one is. So K is going to be the acute, which is less than 90. The reflex, which is greater than 90, but less than 180. That's going to be M, and the obtuse is N, which is greater than 180. Work out the size of each of the angles K, M, and N. Remember that the two triangles are equilateral. So K is 60. Okay, K is 60 because it's one of the angles in the equilateral triangle. Then M, let's just write it in here. So this is now 60 and this is M. M must be 120 because it's a straight angle and the straight angle adds up to 180. So M is 120 And then n is a bit harder. So if m is 120, then this angle here is 120, and this angle here is 120, and in fact this angle here is 60, and this angle here is 60. Okay, so if that's 60 and that's 60, then altogether that's 120. So n is going to be 360 minus 120, which is 240 degrees. Okay, how did I know that was 60? I knew that was 60 because those two lines are parallel. There's a parallelogram, okay, and those two lines there are parallel, and there's a transversal. So these two sides here, these two angles here are alternate to each other. If I turn it on its side, it might be easier to see that. They're alternate, okay, or alternate. The two equilateral triangles are not the same size as each other. Siobhan says the two triangles are similar, but they are not congruent. Give a reason why two triangles are similar. They are similar as they each have 3 angles of 60 degrees. So they are equiangular. Okay? So similar is just about the size of the angles. Give a reason why the two triangles are not congruent. So they are not congruent because they are not exact copies, as the side lengths are different. So one triangle is bigger than the other. Okay, and then there's a construction. Okay, now this one here, this is getting into the circle geometry now. So in the circle geometry, there's a few things we need to look out for. The first thing that's handy to look out for is radiuses, radius. Okay, so when you see a circle and you see lines drawn on it, what you're looking to see is what are the radiuses. So this is a radius, okay, O to E. This is a radius, O to B. This is a radius, O to A, and this is a radius, O to D. So one of the things they want you to look out for is radiuses, because all radiuses are radii. All radiuses are the same length. So of course that might give me some isosceles triangles in a minute if I need them. Oh look, there's one there. Look, that's an isosceles triangle. Okay. We've also got a pair of vertically opposite angles. So if that's 40, that's 40 because those are vertically opposite. So x is 40. And I'm just going to write a note for myself, but they haven't asked you for a reason, but it's no harm to give it. Now, if that's 40, I'm just going to fill in the other angles that I can. So if that's 40 and that's a straight line, then that's 140. There's a straight line. And of course, that's 140 as well, because there's a straight line and they're vertically opposite. Now, how does that help me? Well, I'm going to leave y for a minute, but let's go back to this one here. 140 there is on that arc, isn't it? Now, if I can get a colour. Okay, so that's on that arc. Now, we'd be tempted to say, well, that means that z is half of 140, but if you notice, it's on a different arc. It's not on the same arc. If the line joined here and here, then it would be the same, but it's not, so I can't actually use that. But let's see, is there an angle that is on that bigger arc? So let's make that the arc that z is on. What angle is on that bigger arc? And actually, look, all of this angle is on that bigger arc. All of that one there. So actually, that angle there, which is at the center, is 40 plus 40 plus 140. So that's 220 degrees. So that whole angle there is 220 degrees, which means that z, I'll go down here, z is equal to a half of 220 degrees because it's on the same arc. So z is equal to 110 degrees. That's a hard one because you had to find that new arc. And that's using the theorem that if you have a circle and if you have an angle at the center, it's twice the angle at the edge. This angle here is twice the angle at the edge. So if that's x, that's 2x. And then the follow on from that, the corollary for that, is that if you have a circle and you have a diameter and you draw a triangle with that diameter as the base, that's a right angle, because this is 180, this must be half of 180, which is 90. Okay, so those are the two theorems they're talking about. Let's just go back and finish off with y. So look, y is in this isosceles triangle, and we know this is 40. So we know this angle and this angle are the same. So y, those are both y. So 180 degrees for a triangle minus the 40, so 140 degrees, and then they're both the same size, so I'm going to divide by 2, so y is equal to 70 degrees. Okay, so that's actually quite a good question to work on, because we have isosceles triangles formed by radiuses. We have the angle at the center equal to twice the angle at the edge. We have vertically opposite angles, and we have also a cyclic quadrilateral in there. And just remember that in a cyclic quadrilateral, all the angles add up to 360. But for now, we don't have to worry about that too much, because it didn't come up. Okay? Okay. I'm going to stop this here. I'm going to come back and I'm going to make a second video. So if you've had enough, then you can just finish here. And if not, look for the second video. Okay, bye.